Good evening, class. Welcome to week 3 of Living Systems 1. And this is tonight's lecture, lecture 3, Ionic compounds. So let's think firstly about what we were talking about last week. We were talking about the elements, the way that we see them on the periodic table of the elements, and we were considering each of the elements as just neutral species. That is an atom where the number of positively charged protons is equal to the negatively charged electrons. So overall, there's no net charge. We say zero charge or a neutral atom. But the reality is that most of the elements on the periodic table, or rather many of them don't exist in their neutral state. That's not the most stable arrangement for those atoms. So many of them tend to join together with one or more other atoms, and that joining together is called bonding. So bonding is the joining of two atoms in a more stable arrangement. And let's think back to last week also when we talked about those important electrons that determine the chemical properties of an atom. And those electrons are the valence electrons. So who remembers which electrons are the valence electrons? Where do we find them in an atom? Who remembers that?
Is that the ones on the outermost shell?
Yes, correct. So the electrons are found in the outermost shell that is occupied by electrons. They are referred to as the valence electrons. And these are the ones that tend to participate in chemical reactions. So elements will gain, lose, or share electrons to become more energetically stable. And they tend to do this to attain the electron configuration of the noble gas closest to them in the periodic table. And the reason for this is because the noble gases are already very, very stable. Remember, we said that the noble gases don't tend to react with atoms of other elements. And that's because they already have a very stable arrangement. All right, there's two major kinds of bonding. There are actually many different types of bonding, but the two major ones are ionic bonds and covalent bonds. This week we're going to talk mostly just about ionic bonds, which refer from the transfer of one or more electrons from one element to another. Okay, transfer of electrons. Whereas covalent bonds, which we'll talk about in more detail next week, result from sharing of electrons between two atoms. Okay, so they're the key points. Transferring of electrons from one to the other, or sharing of electrons. All right, so let's consider ionic bonds. When do they form? They tend to form between a metal, which is found, as you know, to the left of the metalloids on the periodic table, with one exception. And what is the exception to the metals rule? Which one? Which? Hydrogen, correct. That's the exception. And so between a metal and a non-metal, as you know, the non-metals are found to the right of the metalloids. And that group also includes hydrogen as a non-metal. So let's take a look here at this example. So here we have sodium, Na, which is a metal, and we have chlorine, which is a non-metal. This is how you would normally find chlorine, as two atoms joined together. Now, sodium, an atom of sodium, tends to join with an atom of chlorine. It's showing two here, but one sodium tends to react with one chlorine to form this compound, sodium chloride. Okay, one sodium and one chlorine. But let's look just briefly at what happens here. Sodium before this joining together or bonding occurs, sodium will actually gain a positive charge, a single positive charge, to form what we call the sodium ion, because it's now charged. And chlorine, an atom of chlorine, will gain a single negative charge. And now instead of... Oh, hello. How are you, Anthony? All right. Chlorine will pick up a single negative charge, as you can see here. And now we don't call it chlorine, we call it chloride, a chloride ion. And I'll explain how that happens in just a minute. Now, we have a single positive charge here and a single negative charge here. And what happens when we have two opposite charges? Well, opposites attract, don't they? So there's an attraction between these two charged species. And that's an electrical attraction, which we call an electrostatic attraction between the two. And the nature of that attraction between the two we call an ionic bond, and that's what brings them together and enables them to join together to form sodium chloride, this compound sodium chloride. Okay, so ions are charged species, so charged atoms that we're talking about, in which the number of protons and electrons is unequal. So let's look at that in a bit more detail, and I need my pen for this. So let's consider 4 protons. Okay, so we have a hypothetical atom here with 4 positively charged protons and 4 negatively charged electrons. Okay, the number of positive charges is equal to the number of negative charges. So what is the overall charge on this particular atom?
So neutral.
Neutral. Neutral, 0 or neutral. Correct. Yep, no charge. Now, let's take this a little bit further. 4 positives. And I should be a bit faster at doing this, shouldn't I? All right, 4 negatives. Once again, 4 electrons. Now, what happens if we lose 1 electron? So we're going to give off 1 electron. What's the overall charge on this atom now?
+1.
+1. This proton here is no longer balanced by an electron. So we say it has a +1 charge, or simply we say plus. Okay? Let's try again. Another example. What happens? Oh, that's an odd one. Okay. So we've got our 4 positives, our 4 negatives, 4 electrons. Now we're going to get rid of or lose 2 electrons. What's the overall charge now on this atom?
2 plus.
2 plus, correct. 2 plus charge, because those 2 protons no longer have a corresponding electron. Okay, good. So this is an easy way to visualize, firstly, loss of electrons and why we say give that corresponding charge. And now we'll go the other way. And instead of losing electrons, we're going to gain an electron. So if this particular atom has gained an additional electron, what would the charge be?
-1.
-1. Correct. -1, because we now have this negatively charged electron that's not balanced by a proton. So the overall charge on this atom is -1. Okay, same thing again. 4 protons. And now this atom is picking up 2 additional electrons. Overall charge would be?
-2.
-2. Okay, excellent. Everyone see that? Everyone follow that?
Yep.
Yes? Elizabeth?
Yep, all good.
All good. Terrific. Okay, so this is always a point of confusion here for students because it's a little bit counterintuitive. Gain of 2 electrons, we say -2. Okay, so that sounds, like counterintuitive, so it's a little bit confusing. But if you picture it like this, then I think it makes a lot more sense. All right, let me clear this.
Quick question, Sylvan.
Yes.
And do shoot me down if I'm jumping ahead a little bit.
Absolutely.
Does, a positive or negative charge change the atom other than the behavior it exhibits, i.e. it wants to become neutral?
Sorry, say that again.
Does the positive or negative charge change the atom itself other
no.
than behavior?
No, that's a good question. So gaining a charge, whether it's positive or negative, does not change the actual identity of the species. Okay, so changing the number of protons does. Remember, it's the number of protons that gives a particular element its identity. But changing the number of electrons does not.
Thank you.
Yeah, good question. Okay, let me clear that. Let's see. Okay, so ionic compounds consist of oppositely charged ions that have a strong electrostatic attraction for each other, which we saw on the previous slide. If we have a sodium with a positive charge, as we saw on the other slide, and we have a chlorine with a negative charge, which we now call chloride, then that attraction here is what we call an ionic bond. That's the nature of the ionic bond, but look at what happens when they come together as a result of that ionic bonding. What is the overall charge now on this compound? On the sodium chloride compound. So sodium has done what to pick up a positive charge? Has it gained or lost an electron?
Lost.
Lost. It's lost an electron. What has the chlorine done to pick up a single negative charge?
Gained an electron.
It's gained an electron. Yes, exactly right. But when you put them together, the positive and the negative, the positive species and the negative species, what's the overall charge now on this compound?
So it's a neutral compound.
It's neutral. It's 0. Yes?
Yep.
So you're taking 2 charged species, they bond to each other as a result of this ionic bonding, this attraction between the opposite charges, and that's why sodium chloride, the compound, is written like that, without any charge indicated, because it's now electrically neutral. Okay, there are 2 types of ions: cations, which carry positive charges, and the anions, which carry negative charges. So up here, sodium is considered to be a cation and chloride is an anion. Okay, so let's now look at this in a little bit more detail. So cations are positively charged ions and a cation will have fewer electrons than it does protons. Let's look at sodium once again as an example. Sodium, as per the information given on the periodic table, has 11 protons, 11 positive protons in its nucleus, and it has 11 electrons. Okay, so that's considered to be a neutral species of sodium. Okay, sodium has how many valence electrons? Here it is down here. If you were to look up sodium on the periodic table, you would see that it belongs to group, it's found in group 1A. And what does that tell us about the number of valence electrons that sodium has?
One.
One, exactly. And here it is. This is the electron dot symbol for sodium down here. So there's sodium with its one valence electron. So remember, sodium has 11 electrons in total, but only one valence electron in its outer shell. Now let's look at the electron configuration for sodium. Here it is down here. The 11 electrons are placed here. The valence shell is shell number 3, and it contains one valence electron, as indicated by the electron dot symbol. Now, this particular valence shell is very incomplete, and this tends to be a very unstable configuration for sodium. So sodium atoms tend to actually expel this one electron. They get rid of that one electron. That's indicated here, loss of one electron, the valence electron. And when that electron is lost, sodium then has still 11 protons, that doesn't change, but now only 10 electrons. So a deficit of one electron, and this is the nature of the positive charge. Sodium with single positive charge, and we now have what's called the sodium cation. But more importantly, let's now look at the electron configuration. Which shell is now the valence shell for sodium? The shell number 2, that's right. N equals 2 is now the valence shell. And how many electrons can you see in the valence shell? In other words, how many valence electrons does sodium have now?
8.
8, that's right. 8 electrons in total, 2 there and 6 there. So now with this filled outer shell, a full outer shell, and the magic number of 8 electrons, and this is a theme that comes up time and time again, sodium is more stable in this arrangement, in its ionic form, its Na+ form. Let's now look at another example. This one is magnesium. This is a common one also. Magnesium has 12 protons in its nucleus, 12 electrons. So this is balanced. This is a neutral atom of magnesium. Magnesium is found in group 2A on the periodic table, which tells us what about the number of valence electrons that magnesium
has 2.
So, has 2, correct. Magnesium has 2 valence electrons. That's indicated here by the electron dot symbol. And now let's look at the electron configuration of magnesium. So the 12 electrons are placed here. The valence shell, as you can see, is shell number 3, N equals 3. And you can see that there are 2 valence electrons in that outer shell. Once again, we have a very incomplete valence shell with only 2 electrons. It's far easier for magnesium just to get rid of them, to lose those 2 electrons. And that's what magnesium tends to do very readily, loses those 2 valence electrons to form the magnesium cation, which has 12 protons and only 10 electrons. So 2 electrons short of being neutral, and that's why magnesium forms this Mg2+, the magnesium cation, because of the loss of 2 electrons. Now let's look at the new electron configuration for magnesium. Once again, you can see the new valence shell is shell n equals 2, and look at the number of electrons there. So we have now a full outer shell. Once again, the magic number 8 electrons in the outermost shell. So by losing 1, 2, or 3 electrons, an atom forms a cation with a completely filled outer shell of electrons. It's not always a completely filled shell. It might be some of the subshells within the shell may be filled. Okay, so just keep that in mind also.
Savannah, are electrons just lost, or are they given to willing recipients?
They're given to willing recipients.
Cool. Okay.
Yeah. Okay, let's look at anions. Anions are the negatively charged ions, and an anion has more electrons than protons. Classic example, once again, is the chlorine atom, which has 17 protons and 17 electrons in its neutral state. Chlorine belongs to, or is found in, group 7A. What do we call the group 7A elements?
Halogens.
Halogens. Very good. Halogens. There we go. Good one to remember. So, because it's found in group 7A, how many valence electrons does an atom of chlorine have?
7.
7. Correct. And here they are. The electron dot symbol for chlorine, surrounded by 7 valence electrons. Here's the electron configuration for chlorine. And now we can see the valence shell. Shell number 3 has 7 electrons, 7 valence electrons. So almost a full, not quite a full outer shell, but almost full subshells. The P subshell is almost full. It's only one short. So chlorine, rather than giving off the 7 electrons, it tends to scavenge 1 electron to fill that P subshell. Very readily gains 1 electron, so that it ends up with 17 protons still, but now it has 1 additional electron, 18 electrons. And this is how the chloride anion is formed. So there's chlorine with a single negative charge, and now you can see it's surrounded by 8 electrons rather than 7. Here we have 8 electrons in the third shell, so the S and the P subshells are filled. And this is the most stable configuration for chlorine. So by gaining 1, 2, or 3 electrons, an atom forms an anion with a completely filled outer shell of electrons, or at least some of the subshells are filled. Okay, the magic number 8 is covered by what's called the octet rule, which states that a main group element is especially stable when it possesses an octet of electrons in its outer shell. Who remembers which groups are the main group elements? The main group. The tall ones, yes. That's a good way of putting it. Yeah, the tall ones. In other words, yeah, groups 1A, 2A, and then 3A through to 8A. Excellent. They're the main group elements. So remember that one. All right, so an octet simply equals 8 valence electrons. And this is a very common theme that you see when atoms of particular elements are losing or gaining electrons. They seem to want to achieve that octet of electrons. All right, so now let's look at how we relate the group number on the periodic table to the ionic charge that's formed for the main group elements. Elements in the same group tend to form ions of similar charge or the same type of charge. Metals form cations. So this is one reason why you need to be able to distinguish the metals from the non-metals. Metals form cations. For those metals in groups 1A, 2A and 3A, the group number is equal to the charge on the cation. In other words, if it's an element that's found in group 1A, then it will form a cation with a +1 charge. Elements in group 2A will form a cation with a +2 charge. So that's an easy one to remember. Non-metals tend to form anions. Okay, the rule for determining the charge, the magnitude of the charge, is a little bit different. For the non-metals in groups 6A and 7A, the anion charge on those elements equals 8, take away the group number. Okay, so they're rules that we can apply to the most common cations and anions. And we'll look at some examples of that right here. All right, so let's start by relating group number to ionic charge for groups 1A to 3A, where the charge on the cation is simply equal to the group number on the periodic table. So group 1A elements, these are metals, and that's denoted here by the letter M. They're group 1A, so we know they have one valence electron. And here's the one valence electron. Okay, these tend to lose that one valence electron. Let's look over here. They lose a valence electron. And that loss of an electron is written here as plus an electron. Just to confuse everyone. All right, I want you to note that when the plus electron is found to the right of this arrow, then it means loss of an electron. Okay, so note that when the plus electron is found on the right-hand side of this arrow, it means loss of an electron. Remember, this is the symbol for one electron. Because one electron's been lost, the group 1A element has picked up a positive charge. Group 2A elements, they're metals, they have 2 valence electrons and they tend to lose the 2 valence electrons. How do we know that? Because it says plus 2 electrons here to the right of the arrow. So these elements pick up a 2+ charge. Group 3A have 3 valence electrons, shown here by the electron dot symbol. The 3 valence electrons are lost. Here they are, plus 3 electrons lost. So these elements pick up a 3+ charge.
Silvana, just to recap, so the group number, metals and non-metals, but even though 3A's got boron, which is a metalloid, same applies?
No, only to the metals, not to the metalloids, yes.
Good, thanks.
No worries. Okay, now let's look at the major anions, which you'll find in groups 6A and 7A. Group 6A elements have 6 valence electrons. What do? They gain 2 electrons. And now we can see the plus 2 electrons is written to the left of this arrow, which means gain of electrons. So 6 plus 2 equals 8. There's our octet of electrons. And this element now has a 2 negative charge because it's gained 2 electrons. Group 7A, these are also common elements that we encounter in the ionic form. They have 7 valence electrons, shown here. They only need 1 more to achieve that octet. So they gain 1 electron. Here it is written here, plus 1 electron. Again, it's written to the left of the arrow, so that means gain of. And now the group 7A halogen is surrounded by an octet, and it's picked up a single negative charge as a result of gaining an additional electron. Okay, and that's all summarised here very nicely in this table. So let's have a look at them. Group 1A elements, sorry, I should say Group 1A metals, and these are the common ones that will form cations with a +1 charge. Group 2A metals will form cations, or mostly form cations with a +2 charge. Then we skip over here, 3A metals, so we start from aluminium, and the other ones are not shown because they don't readily form ions. They're more stable. Aluminium does readily form a cation, a 3+ cation. Then we jump over here to the non-metals. Group 6A non-metals form anions with a 2 negative charge, and the 7A halogens form a single negative charge, as we can see. Okay, so they're the common ones. All right, now we come to the tricky ones. Well, not so much tricky, but we can't apply the same rules to these ones as we just did to the main group elements. All right, so as you can see here, these are metals that form different charges. We'll call them metals with a variable charge. And I want you to remember this slide, slide 14. We'll refer back to this later on, but also you'll need to refer to this particular slide to answer some of your tutorial questions. Okay, so let's look at some examples. Cu, that's copper. It can form a single positive charge. It can form a 2+ charge. Here's another one. This is a good one too. Iron, Fe, can form a 2+ or a 3+ charge. Okay, so we can't apply the group number equals the charge number to these ones, or any other rule. You would just have to refer to this table or look this up online. So metals with variable charges. All right, just briefly, let's look at some of these ions. And here it's shown in the human body, but this applies equally to other animals and also to plants as well. The calcium cation, Ca2+, is found obviously in teeth and bones, but calcium is also an important signalling molecule in plants, very important signalling ion in plants, which you'll learn about next year. Sodium and potassium ions are found in all body fluids. They're equally important in plant cells, both within plant cells and in the fluids surrounding plant cells, particularly potassium, very important. Here's another example. Iron, Fe2+, is present in the hemoglobin of blood, but it's also very important in plants, as you'll learn later on. Chloride, the chloride anion, is present in the gastric juices of the stomach and in other fluids. Once again, the chloride anion is incredibly important in plant processes as well. Chloride is one of the major ions that actually regulates water loss through the pores in the plant leaf, and also the ability of the plant to intake carbon dioxide. Another one, magnesium cation, is needed for nerve transmission and muscle control in animals. But what about in plants? Magnesium cation is a critical component of the pigments required to facilitate photosynthesis, the process of photosynthesis, and hence why magnesium is an essential nutrient for plants. Okay, so we can say that many of the cations and anions are equally important in fish, plants, stock animals such as cows and sheep and so on. All right, now let's look at formulas for ionic compounds, how to determine or how to write the formula. And we've already seen this example here with the compound sodium chloride. Let's have another look at this. Here's sodium, the sodium cation with a single positive charge, chloride with a single negative charge. One of each will actually bond together as a result of that ionic bond between them to form the neutral compound sodium chloride. So we only need one of each to balance the charges. Another example. Now we have calcium, which has a 2+ charge, and we have a fluorine anion here, but now we call it fluoride because it's carrying a negative charge. So we've only got a single negative charge there and a 2+ charge there. What would we have to do to balance the charges in the final compound?
You'd need 2 fluorides to...
Exactly right. Exactly right. So we would actually need 2 fluorides for every 1 calcium to balance the charge. And here it is, shown here, 1 calcium and 2 fluorides, denoted by that number 2 as a subscript. Now we have an electrically neutral compound, calcium fluoride. All right, so let's now look at this a little bit more, how to write a formula for an ionic compound. Step 1, identify which element is the cation and which is the anion. Remember, the metals will form cations, non-metals form anions. Use the group number of a main group element to determine the charge on the cation or the anion. So potassium, it's a metal, group 1A, so it forms a single positive charge. Chlorine is a non-metal found in group 7A. It forms a single negative charge. Someone's playing a bit of music in the background.
Someone's trying to ring me up.
You might want to put that on silent.
Yeah, I just, yeah.
Okay. Calcium is a metal, belongs to group 2A, 2+ charge. Oxygen is a non-metal found in group 6A, so it forms a 2 negative charge. Step 2, determine how many of each ion type is needed for an overall charge of 0 in the final ionic compound that's formed. When the cation and anion have the same charge, as in the charge is of the same magnitude, then only one of each is needed. So a single positive here, a single negative there, so we only need one of each in this compound. Calcium 2+, oxygen 2 negative, only one of each required in this calcium oxide compound to give us a 0 charge. And of course, you already know how to do this. A 2+ calcium cation, but only a single negative for the chloride ion. So of course you would need 2 of these to balance the calcium cation. And that's written as such: calcium 2+ plus chloride with a single negative. And the answer, calcium chloride, but we have 2 chlorides for the 1 calcium. Step 3, to write the formula, always place the cation first and then the anion, and omit the charges, because of course in that compound that's been formed, there are no net charges on the compound. Use subscripts to show the number of each ion needed to have a 0 overall charge. So there's a subscript represented there. When there are no subscripts present, then we assume that there's only one of that particular element, that particular atom. All right, now we're going to move on to naming cations. Naming cations, and the way that we name ionic compounds or ions is a bit different to how we name covalent compounds, which we'll look at next week. Okay, so hopefully I can tease out those differences now for you. Now, when we look at the main group cations, they're simply named for the element from which they're formed. In other words, the name doesn't change, whether it's neutral or whether it's charged. So here we have the sodium cation is simply called sodium, or the sodium cation. So the name doesn't change. Potassium, when potassium is charged, we still call it potassium, or simply the potassium cation. Calcium in its charged form is simply called calcium, and magnesium in its charged form is simply called magnesium, or the magnesium cation, if you like. So they're easy. The name does not change. Now, when we're looking at other cations, it's a little bit different. So remember, they were the main group cations. Main group cations. What about when we're dealing with those cations that have variable charges, those elements that have variable charges? And remember, I mentioned slide 14. Yeah? Everyone remember that? Metals with variable charges. Yep, everyone remembers slide 14? Yes? Okay, so when you're dealing with one of those metals that can form different charges, then you need to actually specify or indicate in the name which one you're talking about. Are you talking about the form, the +2 or the +3 charge? Or are you talking about the single plus charge or the +2 charge, or so on? Okay, so let's look at an example. Now, these metals that form the variable charges can be named in two ways. We can use the systematic name, or we can use the common name. I want you to be familiar with both, because they both seem to come up quite frequently, both systems. Now, with the systematic name, we simply follow the name of the cation by a Roman numeral in brackets to indicate the charge. So here's the metal in question, iron, with a 2+ charge, but iron can also form a 3+ charge. So the way that we indicate that in the name, we simply say the name iron and then 2 in brackets. So this becomes iron 2. In this charged form, it becomes iron 3. So that's quite simple. The common name, using the common name naming method, it's a little bit more complicated. Here we need to actually know where this Fe element symbol is derived from when you use the common naming system. The Fe comes from the Latin ferrum. Now, ferrum becomes ferrous when we're looking at the lower of the two charges. In other words, we drop the UM from ferrum and add OUS, the suffix OUS. For the higher charge, the higher of the two charges, the 3+, ferrum becomes ferric. So drop the UM and add the suffix IC. Okay, so a little bit more involved with naming these particular cations. All right, here's a summary of systematic and common names for some of the metal ions. So we've just looked at iron, which commonly forms 2+ and 3+ cations. Using the systematic name, we name them iron 2 and iron 3. Using the common name, we refer to them as ferrous and ferric. Okay, we can do the same thing here with copper. Copper can form a single positive and a 2+ charge. So we name it according to the systematic naming method as copper 1 or copper 2. And then using the common naming method, we would need to know what the Cu, where the Cu is derived from. It's derived from cuprum. So cuprum becomes cuprous for the smaller charge, and cuprum becomes cupric for the larger of the two charges. Okay, everyone happy with that so far?
Just, I guess it's probably not that important, but
yeah,
I've never heard of, like, I've just had a look. Lead's got 2+ and 4+, but I've never actually heard of that lead being termed in that way.
In which way? With the charges?
You know, with the ick, like cuprous, like
oh, right.
Like I've never heard plumbamus or plum.
You've never heard of it before?
No, not in that referred to. Is that, I guess, you know, yeah.
Yeah.
It's probably not a common one.
It's probably not a common one to be referred to in that way.
Yeah.
But you will see, particularly with iron, with the Fe,
that
is very commonly referred to as ferric and
that's
ferret.
right.
Yeah. So it really just depends on the element itself.
Yeah.
As to how it's commonly referred to.
Yeah.
Good point. Yeah. Okay, so moving on now from the cations, and now let's look at naming anions. So anions are named by replacing the ending of the element name, of the normal element name, with the suffix "ide". So remember earlier on, I was referring to chlorine in its charged form as chloride. And that's why, when it's charged and when it's a negative charge, remember this rule. Chlorine becomes chloride. Bromine in its charged form becomes bromide. And fluorine in its charged form becomes fluoride. Iodine, iodide. Oxygen, it's a little bit different. Oxygen becomes oxide in its charged form. And sulfur becomes sulfide. Okay, so that's just a rule that you have to remember when you actually see a negatively charged atom.
Silvana, do you know if there's if that's actually from the Latin, like the rules about negative and positive? I mean, you may not know.
If that's, I'm not sure about that. If that rule is derived from the Latin, do you mean?
Yeah. So I know someone who teaches Latin. I'll ask him.
Yes. Please let me know.
Will do.
Yeah, that would be very interesting. All right, now let's look at naming ionic compounds once again. But now we're looking at naming that final compound that's formed. So name the cation and then the anion. Don't specify the charge, and don't specify how many ions of each type are needed to balance the charge in the name. Don't specify that in the name itself. This is one of the main differences between naming ionic compounds and naming covalent compounds. So let's look at some examples there. Sodium, one fluoride. One of each is needed in the compound sodium fluoride, and that's simply named sodium fluoride. Next example, magnesium with a 2+ and a chloride with a single negative charge. So you can see what's coming. We need 2 of these for every 1 magnesium cation. So here's the final compound, 1 magnesium and 2 chloride anions. But we simply refer to that compound as magnesium chloride. We don't indicate in the name the number of chlorides that are there. In other words, we don't say magnesium dichloride. Once again, this is a major difference between naming ionic and covalent. So given a particular compound or molecule, you would first have to identify whether it's an ionic compound or is it a covalent compound, because that will determine the naming rules. All right, naming still. How to name an ionic compound that contains a metal with a variable charge. Okay, remember back to slide 14. Give the name for this particular compound here. Firstly, determine the charge on the cation. Yep. Determine the charge on the cation. So that would always be written first. But if you were to actually look up Cu, which is copper, you would actually find that it can form different charges. So how do you know which one it is?
You always look at the anion.
Yes, look at the anion. Absolutely right. Look at the anion, because we know that chlorine forms chloride. The chloride anion, each which has a single negative charge. There are two here, so we can assume from that that the ionic form of this copper ion is 2+. So the copper cation must have a 2+ charge. So that's how you determine that. And I think there is an example in the tutorial questions where you need to do that. Okay, name the cation and the anion. So remember the cation, because it's one of those variable ones, can be named using one of two possible methods. Using the systematic naming system, then Cu2+ can simply be called copper 2. Naming using the common naming method, it becomes cupric. Cuprous, this is from cuprous, becomes, cuprum becomes cupric. And of course, the anion, being chlorine, becomes chloride. And the answer is either copper 2 chloride or cupric chloride. Okay, we're nearly there. Now, just very briefly on the physical properties of ionic compounds. Ionic bonds tend to be very strong bonds, that attraction between two ionic atoms. It's a very strong bond. So you'll see from the numbers here that ionic compounds have some pretty extreme properties. Ionic compounds exist as crystalline solids. That's shown here. There's the crystalline solid. We know it's a solid because the atoms are packed very, very closely in a very orderly arrangement. That's sodium chloride. They have very high melting points. What do we mean by melting point? So it can change from what state to what state?
It's the temperature where the solid becomes a liquid.
Correct. Melting point, changing state of matter from solid to liquid. Yep. And the melting point of sodium chloride is over 800 degrees Celsius. Very good example of how tight these ionic bonds are. Ionic compounds also have extremely high boiling points. What do we mean by a boiling point? A changing state of matter from
liquid to gas.
Liquid to gas. Perfect. Look at the boiling point for sodium chloride. 1,400 degrees Celsius. That's pretty amazing. So given that, if you were given a selection of different compounds and you were asked which one of those compounds had the highest melting point and highest boiling point, what would you look for? You would look for the ionic compound amongst those compounds. Okay, keep that one in mind. All right, when ionic compounds, sorry?
If I may, is that
yeah.
Because how strong their bond is, that's how much energy you need to kind of get the atoms behaving?
Absolutely. I'm shaking my head here. Absolutely right. The stronger the bond between any two species, two or more species, then the more energy has to be put into that system to break those bonds.
Okay.
Absolutely correct. Yes, and we'll talk more about those energy changes in one of our later lectures. Okay, when ionic compounds dissolve in water, they actually separate out into their respective cations and anions. And the resulting aqueous solution will conduct an electric current. So if we take solid sodium chloride, which of course is just common table salt, and dissolve that in water, then look at what happens. The chloride anion will separate from the sodium cation, and those ions will interact instead with the water molecule. Just one property of water that makes it an incredible solvent, the most versatile solvent on the planet. Once again, we will talk more about what we refer to as solvation in a later lecture in more detail. Okay, our final slide, a different group of ions called polyatomic ions. So think about it in this way. Just get my pencil. So the ions that we've been looking at are just single atoms, charged atoms. The sodium ion, the chloride ion, and so on. Yeah. But when we put them together, as such, they're neutral, zero charge. Have a look at these examples here. What's the difference?
They still have a negative charge, so they're not neutral.
They're still carrying charges. These ones are still carrying charges. And there's another difference too. These ionic species consist of more than one atom. Only one atom up here, one atom up here. That's what we've been considering. These are ions that carry an overall charge, whether that's or mostly negative, that we see here. I think they're all negative. They are all negative. And they consist of more than one atom, but there's another important difference here. These atoms that you see in this table here, they're actually bonded together not by ionic charges, but by, not by ionic bonds, but by covalent bonds. So another important difference. They're actually joined together by a different type of bond. And we'll look at those next week. Okay, polyatomic ion is a cation or anion that contains more than one atom. It carries an overall charge, and the atoms are bonded together by covalent bonds, not ionic bonds. Let's look at some of these. So polyatomic ions of carbon. Some of these are more important than others. So for anyone doing animal studies, these two polyatomic ions, carbonate and bicarbonate, will become important in your learning of physiology in animals when you do animal anatomy and physiology. Here's another polyatomic ion of carbon called acetate. Here's one that everyone's probably familiar with, the cyanide ion. Everyone heard of cyanide?
Yeah. Yep.
Yeah. Pretty horrible poison, yes. And who knows where you would find cyanide naturally?
Almonds?
Almonds, yes. Yes.
Yeah.
Seeds, many seeds contain cyanide, absolutely. Okay.
Why is the negative on the left in that one?
Yeah, I'm not really sure why sometimes it's written to the left.
Okay.
That's a good question, one that I've wondered at myself. I tend to like to write them on the right, probably because I'm very right-handed. But yeah, sometimes you do see it written to the left.
Looking at the two that are on the left, hydroxide and
the hydroxide and the cyanide, yeah.
But different suffix to the others as well.
Yes. Yeah, that's a good one. Good one to look into.
Okay.
Yeah, I'll have to actually do some reading on that.
Okay.
Good point, yeah. Okay, nitrogen. Polyatomic ions of nitrogen. These two are really important for everyone, regardless of whether you're doing viticulture and winemaking, agriculture, agronomy, or aquaculture. These will come up all the time. So they're good ones to commit to memory: nitrate, NO3 minus, and nitrite. Okay, what's the difference between those two? Nitrate and nitrite.
Well, the nitrogen's got a different charge on it. So I guess if you start isolating not the nitrogen and the oxygen.
Yeah. Well, they both carry the same charge. They both have a single negative charge. There's something else that's different between them.
Extra oxygen.
Correct.
Yeah.
Correct. So nitrate has 3 oxygens. Nitrite has 2 oxygens. And this actually determines the suffix that's used, ate or ite. Okay. So the species that has more oxygens is given the suffix ate, fewer oxygens, ite. Okay, so they become very important for everyone. This one's also important. OH with a negative charge. This is called hydroxide, and we'll refer to this a lot in both Living Systems 1 and 2, and I'm sure you will also in some of your other subjects. Another very important one that we refer to a lot, the phosphate, polyatomic ion. And this one here, sulfate and sulfite. These two will become very important for winemaking students, and you'll visit them in great detail in wine chemistry in your second year if you're doing viticulture and winemaking. Okay, so that's it for tonight.
Yep.
How's everyone feeling about that?
Yeah, pretty good.
All good?
Yeah.
Yep.
So next week we've got the same thing.
Same thing next week, yes,
Okay.
online class. Now, before you go, let me know if you've got any questions. But before you go, tutorial questions based on tonight. Okay, as you can see, these tutorial questions are not assessed. Okay, not assessed. But having said that, I always say to students, please treat them as being just as important as the assessed tutorial questions, because of course all the subject material will also be tested or examined. So work your way through these. You'll find questions on tonight's lecture, ionic compounds, and also questions on next week's lecture, covalent compounds. So you might want to leave these until next week, part 2 of these questions. And in order to check that you're on the right track, there is an online quiz for these tutorial questions. But of course, the online quiz is not assessed. But of course, you can go on there and put in all your answers, make sure that you're understanding everything. Now, with the non-assessed online quizzes, you can have as many attempts as you like. Okay, you're not limited to only the 2 attempts.
So do we need to submit them though, or do we still need to submit them?
Yes, I think you still need to submit at the end of each attempt so that then you can go on to your next attempt.
Okay, all right.
Okay, but don't worry, you're not assessed on those ones.
Okay. Yep. All right.
Okay, all right, so make sure you get through those, and that's it for tonight. Are there any other questions?
I do have one, Silvana. Based on what you just said,
Yep.
you've been doing the quizzes online for the other ones. Is that not
Yes.
the way we're supposed to do the assessed ones?
Yes, it is how you do the assessed ones also.
Sorry, only because you said you do the online quiz just to test yourself out, but is this for these non-assessed ones?
That's just for the non-assessed ones,
okay.
Yes. So obviously the ones that you did last week and the week before, they were both assessed. Okay.
No.
And of course, they're always submitted via the online quizzes.
Thank you.
You're welcome.
All right. I could be I may struggle to get to next week's class, but yeah,
Okay.
that shouldn't be a problem. I can go through the notes anyway.
Absolutely, absolutely. And I always record these classes just in case you can't make it, which some students can't.
Yeah. Yeah.
So you can always listen to the recording also.
Yeah. All right. No worries.
Yeah.
Thank you.
Okay. Thank you.
Thanks a lot.
Thank you.
No.
See you next. I'll see you next week.
Will do.
Bye.
All right. Bye.
Bye.
Bye.